In this video, we'll be discussing the solution of a simple problem from the design of helical springs based on the analysis we made in the previous video. So we are knowing the procedure for designing the helical springs and we'll be solving it one by one. So here a helical spring is subjected to a load of 800 Newton. So we are having the value of the force F that is acting on the helical springs, which is F equal to and 800 Newton, and under this load it deflects by 40 mm. That means the deflection Y is also given, which is equal to 80 mm, and the diameter of each coil is 10 times that of wire. That means we are denoting the wire diameter by small d and the diameter of the coil is capital D, and the ratio of this d by d is given, which is 10. Actually this ratio is known as spring index, which is C. We have already seen in the previous discussion. So the value of C is given. C value is equal to 10. Here the allowable shear stress within the spring material is also given. So the toe allowable is 350 megapascal or 350 into 10 raised to 6 pascal or Newton per meter square. And the rigidity modulus capital G is also given, which is 84 GPa or 84 into 10 raised to 9 Newton per meter square. So these are the given values. Based on this one, we will be solving. So we are already knowing under the action of this force, the shear stress will be produced in the spring material, and we have seen the expression, that is 8FD divided by pi d cube into some correction factor by considering all the combined effects and the curvature effects, that is K, which is known as Wahl's shear stress factor. I will be showing you this equation in the data book. So this is the design procedure. Here we will be first finding the diameter, that is small d, of the wire. Here only the capital D and small d ratio is given. From that we will be finding the wire diameter, then we will be standardizing it, then we will be assuming some suitable end condition, and we will be finding the number of coils I, then this free length will be evaluated, pitch will be evaluated, and finally the spring stiffness will be evaluated. So this is the equations, or this is the procedure. The equations are given here. So we will be needing this equation, that is the torsional shear stress 8FD by pi d cube into K. So we need to obtain the value of K here. So K is a function of C, spring index. Here we are having the spring index value as 6. So if C is 6, then K will be equal to 4C, 4 into 6 minus 1 divided by 4 into 6 minus 4 plus 0.615 divided by C. By 6 here, because C is 6. So you will be getting a value of 1.145 for the value of K. So the same expression I will be applying. So this will be the this will be the other tables required. So here I will be writing the tau max. So tau max for the spring material is, equation is 8FD divided by pi d cube into capital K. So this capital K value we have evaluated Wahl's shear stress factor, which is 1.145, and the F value we are already having. So this F is equal to 800 Newton, and here we are having the term, that is d by d cube. I can write this d by d cube as d by d divided by d square. I can write like this. So this d by d is actually C, and its value is 10 divided by d square, like this I can write. Then only variable will be d square. So I can find the tau max from this expression, which is 8 into F is 800 Newton into d by d cube will be replaced by this thing, that is into 10 divided by d square pi into K. K value is 1.145. So this is the entire expression for the tau max, and this can be equated for the limiting condition with respect to the toe allowable. In limiting condition we will be replacing this less than or equal to by equal sign, and the allowable shear stress is 350 megapascal. I will be substituting it in 350 as such. That means I am using a unit of Newton per mm square, and here I am using a unit of Newton. Then this value will be getting in units of mm square, or D will be getting in units of mm. So we have to solve for this d from these above equations by equating to this 350. So if you are solving, the value of d will be getting around 8.16 mm from this above criteria. So this is the spring wire diameter obtained from the this criteria. So we need to standardize this value. So for standardizing, we will be looking for the table, this table, that is table 11.2 will be looking for, and this 8.16 is coming which step we are seeing. So if we are looking onto the first column, which is cauldron wire unalloyed, you can take any type or hardened and tempered, or you can take stainless steel, any column you can take. So I am going for the first column, and here our value is 8.16 mm. So we need to look for in which step it is lying. So if you are looking onto these values, that is 6.5 to 11 and hyphen 0.5 means 0.5 is the step for that range. That means in the range of 6.5 to 11, the standard values will be 6.5, 7, 7.5, that is in the ranges of 0.5. So our 8.16 will be coming in the range of 8 and 8.5. So we need to take the higher standard value. So we will be standardizing our wire diameter to 8.5 mm. So finally our standardized wire diameter will be equal to 8.5 mm. So this is after the first step, or the you can call it as the second step. So from the this standard wire diameter, I will be calculating the capital D, that is the mean coil diameter. So this is the mean coil diameter. So this D is equal to this spring index C into small d. So I can write here 0.5 into 10, which is equal to 85 mm. And for the same coil, I can calculate the inner diameter capital Di, which is D minus small d, and the D outer diameter, which is capital D plus small d. If you are substituting this value properly, then this will be getting as 76.5 mm, and this will be 93.5 mm. So this is the end of second step, where we are standardizing the diameters and we are finding the other diameters, that is mean coil diameter, the inner diameter of the coil, and the outer diameter of the coil. Next we need to find the number of active coils. Already I have explained the difference between active coils and the total coils. Active coils are the number of coils involved in the compressive action. So for finding the active number of coils, I will be using this expression. So here the expression for y I will be using, because deflection y is given, so I can rewrite for I. I is the number of active coil. I can rearrange this I as I equal to y into GD divided by 8F C cube I can use. So here all values are known. Y is given as, the deflection is given in mm, which is 40 mm. The force value we are having, F we are having, C value we are having, G rigidity modulus is also given, diameter is also known. So I will be substituting these values or using this expression, that is again I am writing the number of, this is the number of active coils. So active coils is equal to y into G into D divided by 8 FC cube. Here I will be substituting the values in mm and Newton per mm square. So this is 40 mm. Rigidity modulus 84 GPa, or 84 into 10 raised to 3 megapascal, or Newton per mm square. That is I am using. And the standardized wire diameter, which is 8.5 mm divided by 8 into F is 800 Newton given, and C value is 10, so it is 10 cube. If you are solving, we will be getting this I as 4.63. But this I is representing the number of active coils, so we will be rounding it to the next full number, that is we will be rounding it to 5. So the active number of coils is, or the turns is 5. So the next step is we need to select a suitable end condition, or the end construction we need to select for this spring. So we explained the different end conditions in the previous video. So that end condition is can be obtained from this table 11.4. Here any end condition you can select, the plane end or ground end or square end, or the square and ground end you can select. Here we will be selecting the square and ground end. That means here we will be focusing on to the last one, and the last condition is given in this last column of this table D, that is square and ground end. So here if the active number of coils is I, then the total number of coils is given by I plus 2. So for this spring I can write here, I am selecting the square and ground ends construction I am selecting. So this is the assumption, any type you can select, then we are having the IT, that is the total number of turns is equal to I plus 2, that is from this table. So 5 plus 2 will be equal to 7. So this is the total number of coils, and from the same thing we will be finding the free length. So free length is denoted by L0, and that we will be seeing from the same table expression we will be seeing. So the free length is obtained from this table, that is this expression, the right hand side expression we will be looking for, that is I plus 2 into D into Y plus A I will be explaining, that is I plus 2 into wire diameter D into deflection Y plus A, and this is known as axial gap. I will be explaining how to consider the axial gap. So this one we can evaluate. I is 5 and 5 plus 2 into D, that is in 7 into 8.5 plus Y is 40 mm, and plus axial gap we are calculating it as I minus 1 into 1 mm per coil. That is the see, if in the compressed length there will be gap within the coils, and that you can take this empirical relation. Commonly for finding the A value we are using this expression. If you are substituting it properly, then finally, that is I is 5, 5 minus 1 into 5. If you are substituting it properly, finally we will be getting the free length of the spring as 95 mm. So this is the value of the free length. Then we need to find the next step is we need to find the pitch of the spring. That can also be obtained from the above table. So we will be looking for this end condition table. So pitch is obtained from the last column. So pitch is equal to free length L0 minus 2D divided by I, that is the active number of coils. So pitch is equal to L0 minus 2D divided by I. If you are solving, you will be getting the value of 15.6 mm will be the pitch. So you can round it to the next 16 mm can be used for this helical springs. Final step is we need to calculate the spring stiffness or the spring constant, which is defined as the force per deflection, force required for unit mm deflection. So this value is already we are having, which is 800 Newton divided by Y is 40 mm. So this value will be in units of Newton per mm. So this is actually 800 by 40. This will be getting us 20 Newton per mm, or 20 into 10 raised to 3 Newton per meter, which is 20 kilonewton per meter actually. So this is the spring index. That means for producing a unit deflection of 1 mm we require 20 Newton. So this is the simple procedure or a simple type of problems from the design of helical springs. Here the load as well as deflection was given, and also spring index, that is the capital C, D by D ratio was also given. From that we first evaluated the diameter value, the wire diameter, then we standardized it, then we found the values of these diameters, coil diameters. From then we have evaluated the number of active coils I. Then we have assumed a suitable N condition from that table, and that same table we are used for evaluating these things: total number of coils, free length, pitch, and finally the spring constant. So this is the procedure for solving such a simple problem from the design of helical springs.